No human being will ever reach the nearest star. The farthest any human being has ever travelled from Earth is about 250,000 miles. That was in 1970, during the Apollo 13 mission, when 3 astronauts swung around the far side of the moon and for a few minutes were farther from home than anyone in history. They could not see Earth. They could not hear it. They were alone in a damaged spacecraft at the very limit of what the human body and human courage could endure. That distance, 250,000 miles, is enormous by any earthly standard. It is farther than most people will travel in a lifetime, but measured against the scale of the universe, it is almost nothing. The nearest star beyond our Sun is over 25 trillion miles away, a distance so vast it stretches beyond any single human lifetime. The edge of our own galaxy is so distant that light itself takes 100,000 years to cross it, and the observable universe extends in every direction farther than any number can make feel real. Humans are not built for these distances. We are fragile. We are mortal. We carry with us the need for air, for water, for food, for warmth, for gravity, for companionship, for meaning. We cannot survive the radiation that fills interstellar space. We cannot endure the decades or centuries that even the fastest conceivable spacecraft would need to reach another star. We are, in the most fundamental sense, creatures of Earth. Our bodies evolved here, our minds evolved here, and everything about us, from the calcium in our bones to the rhythms of our sleep, is calibrated to a world we cannot take with us. But we're also creatures of curiosity, and curiosity does not respect the limits of the body. It reaches farther than any hand can stretch, it travels faster than any foot can walk, and it has found a way to send itself into the places where we cannot go, not in flesh, not in bone, but in silicon, in metal, in code, in the quiet, tireless patience of machines. This is a story about the travellers we are building to go where we never can. If you enjoy these stories and would like to help the channel grow, I would be truly grateful if you subscribed. It makes a real difference. Everything humanity has ever seen with its own eyes, every landscape, every horizon, every glimpse of the cosmos through a window or a visor, fits within a tiny sphere centered on our small blue planet. The Moon is the farthest we have been. Mars, the next plausible destination, is at its closest about 34 million miles away, roughly 140 times the distance to the Moon. At the speed of current chemical rockets, the journey takes 7 months. 7 months in a metal container, breathing recycled air, watching your muscles weaken and your bones thin. 7 months, and you have only crossed a sliver of the solar system. The outer planets are farther still, each one a step deeper into the cold. Jupiter, the nearest of the giants, is close to 500 million miles from Earth. Saturn lies nearly twice as far, and Neptune, that dim blue world at the edge of the known solar system, drifts almost 3 billion miles from the Sun. These are distances that resist imagination. If you could drive a car at highway speed without stopping, day and night, year after year, it would take you over 5,000 years to reach Neptune. No human being has ever visited these worlds. No human being is likely to. The distances are simply too great, and the human body is simply too frail. And then there is the space beyond the planets, the Kuiper Belt, that vast ring of icy bodies where Pluto drifts in its slow, cold orbit, the Oort cloud, a hypothetical shell of comets that may extend halfway to the nearest star, and then, finally, after all of that, the interstellar medium, the space between the stars, a void so empty that a single atom of hydrogen drifts alone through every few cubic centimeters. This is the ocean that separates us from everything else in the galaxy, and it is an ocean that no human body is equipped to cross. To understand how vast this ocean is, consider the boundary of our own solar system. The Sun's gravitational influence extends roughly 2 light-years in every direction to the outer edge of the Oort cloud. If the solar system were the size of a coin, a small silver disk resting on a table, then the nearest star would be another coin sitting across the room, and the galaxy would be the size of the continent. We have explored the coin, we have sent robots to its edges, but the room, the building, the continent beyond, all of that remains untouched. The Voyagers are the first objects to step off the coin's edge. They are falling toward the floor, slowly, in the direction of the far wall. They will not reach it. But they have shown that leaving the coin is possible. The human body is a marvel of engineering, but it was engineered for a very specific environment. We need a narrow range of temperature. We need a particular mixture of gases to breathe. We need water every few days and food every few weeks. We need protection from radiation, from vacuum, from the cold that would freeze us solid in minutes. We need gravity or something like it to keep our bones dense and our hearts strong and our blood flowing in the right direction. And we need time, not too much of it, because we age, we wear down, and eventually we stop. A journey to the nearest star, Proxima Centauri, at the speed of the fastest spacecraft ever launched, would take roughly 73,000 years. That is longer than all of recorded human history, longer than the time since the last ice age, longer, by a wide margin, than the entire existence of human civilization. No one can live that long. No ship can carry enough food and water for that long. No body can withstand the accumulated radiation of deep space for that long. The distance to the nearest star is not merely a challenge, it is a wall, and no amount of human endurance can climb over it. Consider another way of feeling that distance. If you could somehow walk to the nearest star, stepping 1 foot in front of the other at a comfortable pace, 3 miles per hour, and you never stopped, never slept, never rested, you would walk for about 5 billion years. That is roughly the age of the Earth itself. You would need to walk for the entire history of the planet, from its formation out of dust and gas to this very moment, just to close the gap between here and the nearest light in the dark. And the Milky Way contains perhaps 200 billion other stars, most of them far more distant. The galaxy is not a neighbourhood, it is an ocean, and we are standing on the shore looking out. Even with faster propulsion, the numbers remain daunting. If we could build a spacecraft that travelled at 10% the speed of light, an achievement far beyond our current technology, the journey to Proxima Centauri would still take over 40 years. A person who boarded such a craft at age 30 would arrive in their 70s, having spent the best decades of their life sealed inside a vessel smaller than a house, surrounded by the same few faces, breathing the same recycled air, with nothing outside the windows but the unchanging darkness of interstellar space. It is conceivable, it is not desirable, and for destinations farther than the nearest star, even this heroic speed is not enough. There is a deeper problem still. The human mind is not designed for the kind of patience that interstellar travel requires. We think in days, in weeks, in years. We plan in decades, at most. A journey measured in centuries is not something we can meaningfully undertake, because no individual can hold that thread for long enough. A generation ship, a vessel designed to carry a self-sustaining community across the void, with children born and raised and dying aboard, is a thought experiment that reveals more about the limits of human psychology than about the limits of engineering. We are creatures of seasons, of urgency, of now. The spaces between the stars demand a traveller of a different kind. We have already begun to send such travellers. In 1977, 2 spacecraft called Voyager 1 and Voyager 2 were launched from Cape Canaveral on a mission to study the outer planets. They visited Jupiter, Saturn, Uranus, and Neptune, sending back images and data that transformed our understanding of the solar system. And then, their primary missions complete, they kept going. Voyager 1 is now almost 16 billion miles from Earth. That is so far that a radio signal, travelling at the speed of light, takes nearly 24 hours to reach it. If you sent a message to Voyager this morning, the earliest you could hear a reply would be the day after tomorrow. Later this year, the spacecraft will reach a distance of 1 light day from Earth, a milestone that no human-made object has achieved before. It is the farthest thing we have ever built, and yet, measured against the distance to the nearest star, Voyager 1 has barely left the driveway. After almost 50 years of flight, it has covered less than 1/500th of the distance to Proxima Centauri. At its current speed, roughly 38,000 miles per hour, it would take another 73,000 years to get there. Voyager will never reach another star, at least not one that anyone alive today or anyone born in the next 1,000 generations will know about. But that is not the point. The point is that it is still going. It does not eat. It does not sleep. It does not grow lonely or afraid. It does not need to come home. It simply travels, powered by the slow decay of plutonium, sending back data in a whisper that grows fainter every year, but that has not yet fallen silent. Voyager carries no artificial intelligence. It is, by modern standards, a simple machine with less computing power than a pocket calculator. Its instructions come from Earth, sent by engineers who must wait nearly 2 days for a round-trip confirmation. It navigates by the stars using sensors that were designed in the early 1970s. It is a messenger in a bottle, thrown into the ocean of space with a golden record strapped to its side, carrying greetings in 55 languages, music from Bach to Chuck Berry, and the sound of a human heartbeat. It is beautiful, it is brave, and it is the first draft of something much larger. The golden record is perhaps the most hopeful object ever made. It was assembled by a committee led by the astronomer Carl Sagan, who understood that the chances of anyone ever finding it were astronomically small. But he made it anyway. He chose the music. He chose the images. He chose the greeting in which a child says, in English, "Hello from the children of planet Earth." He included a diagram showing the position of our sun relative to 14 pulsars, a kind of cosmic return address, etched into the cover of the record in a language that any sufficiently advanced civilization might understand. The record will last for 1 billion years in the vacuum of space. It will outlast every human language, every nation, every religion, every culture that exists today. It is a time capsule addressed to no one in particular, a quiet act of faith in the idea that the universe is not as empty as it looks. Sometime in the next few years, Voyager's power will fade below the level needed to operate its remaining instruments. The last data will be transmitted, the last command will be acknowledged, and then silence. The spacecraft will continue on its trajectory, moving through the interstellar medium at 38,000 miles per hour, but it will no longer speak. It will become an artifact, a fossil of human ambition, drifting through the galaxy like a seed carried on the wind long after the plant that released it has gone. Imagine a traveller that does not need air, that does not need food or water or sleep, a traveller that does not age, that does not grow bored, that does not miss its family or count the days until it can go home, a traveller that can endure the radiation of deep space without flinching, that can operate in temperatures close to absolute zero, that can wait for decades or centuries without losing its purpose or its patience. A traveller that can think, not in the way that you and I think, with emotion and memory and the weight of lived experience, but in the way that a river thinks, following the path of least resistance, finding solutions to problems it was never explicitly taught to solve. This is what an artificial intelligence in space would be. Not a robot in the science fiction sense, not a humanoid figure with feelings and fears, but a system. A network of sensors, processors and actuators housed in a shell designed to survive the most hostile environment in the known universe, equipped with the ability to observe, to analyze, to decide, and to act. Without waiting for instructions, without needing permission, without ever needing to rest. It would not know loneliness. It would not know wonder, but it would do the things that wonder asks of us. The machines we send into deep space today are already beginning to demonstrate these capabilities. The Perseverance rover on Mars uses onboard algorithms to identify interesting rock formations and choose which ones to study, without waiting for a scientist on Earth to tell it what to look at. ESA's Hera spacecraft, launched in 2024, navigates to its asteroid target using principles borrowed from self-driving cars. JPL has developed a snake-like robot called ELs, designed to slither into the crevasses of icy moons and search for signs of life in places no wheeled rover could reach. These machines are not fully autonomous. They still rely on human oversight, but with every mission, the tether grows longer, the leash loosens, and the machines move a little farther from the hand that launched them. Before we send AI to the stars, we will send it to the ocean worlds of our own solar system. Europa, a moon of Jupiter, hides a liquid ocean beneath a shell of ice. Enceladus, a moon of Saturn, shoots geysers of salt water into space from fractures in its south pole. These worlds are among the most likely places in the solar system to harbour life, and they are places where human explorers cannot easily go. Jupiter bathes Europa in enough radiation to kill an unshielded human in hours. The ice shell may be miles thick. The ocean beneath is pitch black, pressurized, and cold. This is not a place for people, but it may be a place for machines, autonomous submarines equipped with AI that can navigate without GPS, communicate without radio through miles of ice, and recognize signs of biology without a biologist on call, are already being tested in the deep oceans of Earth. The leap from the Mariana Trench to the oceans of Europa is enormous, but it is a leap of engineering, not of principle. The minds that will explore those alien seas are being trained right now in the dark waters of our own world. The case for sending artificial intelligence to the stars is not just practical. It is, in a sense, inevitable. As our ambitions extend beyond the solar system, the communication delay with Earth becomes not an inconvenience, but an impossibility. A spacecraft at Proxima Centauri would be over 4 light-years from Earth. A question sent from mission control would take 4 years to arrive, and the answer would take 4 years to return. An 8-year conversation. By the time you learned that something had gone wrong, the problem would be 8 years old. By the time your advice arrived, it would be 8 years out of date. No meaningful exploration can happen at that pace. A spacecraft at another star must be its own mission control. It must carry within itself the knowledge to interpret what it finds, the judgment to prioritize what matters, and the ability to adapt to the unexpected. It must be, in the functional sense of the word, intelligent. Not because intelligence is a luxury, but because at those distances, intelligence is survival. What would such a spacecraft look like? It would be small. Every gram matters when you're accelerating something to a significant fraction of the speed of light. It might be no larger than a toaster, a chip of silicon and carbon fiber carrying a suite of miniaturized instruments, cameras, spectrometers, magnetometers, particle detectors. It would be powered by a thin sail, perhaps a few meters across, pushed by a beam of light fired from an array of lasers in orbit around Earth. This is not fantasy. The Breakthrough Starshot initiative, funded by the late physicist Stephen Hawking and the investor Yuri Milner, proposed exactly this concept: a fleet of tiny, light-propelled probes that could reach Proxima Centauri in roughly 20 years. 20 years, not 70,000. 20. The probes would arrive at another star system with no way to slow down. They would streak through at a significant fraction of the speed of light, taking measurements and photographs as they passed, then continue on into the dark. The encounter would last minutes, but in those minutes, they could gather more data about an alien star system than a century of telescopic observation from Earth. And because they would be small and cheap enough to send in large numbers, the loss of any individual probe would not be catastrophic. If one fails, the others continue. If 10 fail, the others continue. It is exploration through redundancy, a swarm of tiny minds flung across the void, each one carrying a fragment of human curiosity into a place where human bodies can never follow. The moment of launch would be quiet, not the thunderous, earth-shaking departure of a chemical rocket, but something subtler. A beam of light invisible to the naked eye fired from an array in orbit, striking a sail thinner than a human hair. The sail would accelerate rapidly, reaching its cruise speed within minutes, and then it would be gone. No flame, no roar, just a tiny mote of matter riding a beam of light, heading toward a star that would not grow noticeably brighter for years. The people who launched it would know that they would not live to see it arrive. Their children might not live to see it arrive. But someone, someday, would receive the data, and that would be enough. This willingness to invest in a future you will never see is one of the most remarkable qualities of the human species. We plant trees whose shade we will never sit in. We build cathedrals that take centuries to complete. We write music that will be performed long after the composer is forgotten. Sending a probe to another star is the ultimate expression of this impulse. It says, the answer matters more than who hears it. The question is worth asking even if we are not the ones who receive the reply. But the swarm is only the beginning. Beyond the quick flyby missions, there is a slower, deeper kind of exploration that only machines can undertake. Imagine a spacecraft not designed for speed but for endurance. A vessel that does not rush past its destination but enters orbit, deploys instruments, and studies an alien system for decades, for centuries, for longer than any human institution has ever persisted. Such a spacecraft would need to repair itself. Components degrade, circuits fail, micrometeorites puncture shielding. Over centuries, even the most robust hardware will wear down. The spacecraft must carry the ability to diagnose its own ailments and fabricate replacement parts, perhaps using raw materials gathered from asteroids or moons encountered along the way. This is not idle speculation. 3D printing in space has already been demonstrated on the International Space Station. The principle of in situ resource utilization, using materials found at the destination rather than carrying them from home, is central to every serious plan for Mars colonization. Extending this principle to an interstellar probe is a natural step, albeit one that requires technology we have not yet built. The artificial intelligence aboard such a vessel would need to be far more sophisticated than anything that exists today. It would need to understand context, to weigh competing priorities, to make decisions that its creators could never have anticipated. It would need something that we might, if we are being generous with our language, call curiosity. Not the human kind, tangled with emotion and desire, but a functional analogue. A drive to investigate, a bias toward the unknown, a tendency, when faced with two paths, to choose the one that leads somewhere new. Consider what an AI probe would need to do when it arrives at an alien star system. It would need to survey the system, identifying planets, moons, asteroids, and other bodies. It would need to choose which of these to study more closely, a decision that depends on mission priorities, available resources, and what the initial survey reveals. It would need to interpret data that may not match anything in its training set, a chemical signature it has never seen before, a geological formation that follows no known pattern, an atmospheric composition that hints at something its creators did not predict. In each case, it would need to decide, is this important? Should I spend more time here? Should I change my plan? These are not simple calculations, they are judgments, and making them well, millions of miles from anyone who could help, is the central challenge of interstellar AI. Some scientists have imagined a network of relay probes, a chain of small stations spaced along the route between the Sun and a distant star, each one receiving signals from the probe ahead and amplifying them before passing them back toward Earth. Such a relay network would solve one of the fundamental problems of interstellar communication. The farther a signal travels, the weaker it becomes. A probe at 4 light-years would need to shout very loudly for Earth to hear. But a probe at 4 light-years passing its message to a relay at 3 light-years, which passes it to another at 2 and another at 1, could speak in a whisper. The cost of building such a network would be immense, but the concept illustrates a broader point. The machines we send to the stars need not be alone. They can be part of a system, a web of intelligence stretched across the void, each node supporting the others, each one extending the reach of all. Over centuries, the spacecraft would accumulate a vast archive of observations. It would study stars, planets, moons, asteroids, comets, dust clouds, magnetic fields, radiation environments. It would map the territories between the stars with a patience and thoroughness that no human expedition could match. And periodically it would turn its antenna toward a faint blue dot far behind it and transmit its findings, a signal that would cross the void at the speed of light, arriving at Earth years or decades later, carrying news from a place that no human eye has ever seen. There is a version of this future in which the probes do not merely explore, they build. The concept of a self-replicating probe, sometimes called a von Neumann probe after the mathematician John von Neumann, imagines a machine that arrives at another star system, gathers raw materials from asteroids or moons, and constructs a copy of itself. That copy is launched toward the next star, where it arrives, gathers, builds, and launches again. Through this process, a single initial probe could, over millions of years, spread to every star in the galaxy. The idea is staggering in its implications. It means that the exploration of the entire Milky Way is, in principle, a finite project. Not a project that any human will see completed, but a project that, once begun, completes itself. A thought released into the universe that thinks its way forward, one star at a time, long after the mind that first imagined it has gone. What would they find, these quiet travellers? We can only guess. But the guesses are extraordinary, and even the act of guessing, of imagining what might be out there, is itself a kind of reaching. Around Proxima Centauri, there is a planet. Proxima Centauri b, discovered in 2016, is roughly the mass of Earth and orbits within the habitable zone of its star, the region where liquid water might exist on the surface. We know almost nothing about it. We do not know if it has an atmosphere. We do not know if it has water. We do not know if it is a barren rock, a frozen wasteland, or something else entirely. It is just over 4 light-years away, close enough to be tantalizing, far enough to be unreachable by any human mission we can currently conceive, but a robotic probe, travelling at even a fraction of the speed of light, could get there within a human lifetime. It could photograph the planet's surface. It could analyse its atmosphere. It could search for the chemical signatures of life. And it could send that information home across 25 trillion miles at the speed of light. Farther out, there are other candidates. TRAPPIST-1, a system of 7 Earth-sized planets orbiting a dim red star about 40 light-years away. Kepler 442b, a potentially habitable world about 100 light-years distant, and thousands more scattered across the galaxy, identified by telescopes but known only as points of light and columns of data. Each one is a question. Each one is an invitation. And for each one, the answer is the same. We cannot go. But we can send something that can. The question of what these probes might find if they detect life is one that scientists and philosophers have debated for decades. If an AI probe arrives at another star and finds a barren, rocky world with a thin atmosphere and no organic chemistry, that is a result. An important one. It tells us something about the prevalence, or the rarity, of the conditions that gave rise to life on Earth. But if a probe detects something else, an atmosphere rich in oxygen and methane, chemicals that should not coexist unless something is producing them, a surface with patterns that suggest growth or structure, then the discovery would be the most significant in the history of our species, and it would have been made not by a human being, but by a machine that was designed, built, and launched by human beings who knew they would never live to hear the answer. There is a beautiful asymmetry in this. The generation that builds the probe is not the generation that receives the data. The people who ask the question are not the people who hear the answer. This is exploration on a timescale that transcends any individual life. It is a gift from one generation to another, a letter posted across the decades, arriving long after the sender has gone. And the machine that carries it does not know that it is a gift. It does not know that it matters. It simply does what it was built to do, steadily, faithfully, across the dark miles. There is a quality to interstellar space that is difficult to put into words. It is not just empty. It is the purest form of emptiness that exists. Between the stars there is almost nothing. A few atoms of hydrogen per cubic inch. A faint wash of cosmic radiation. The occasional grain of dust, smaller than a cell, drifting through a darkness so complete that the word darkness does not do it justice. There is no sound because there is nothing to carry it. There is no weather because there is no atmosphere. There is no change because there is nothing to change. It is the stillness at the bottom of everything, the silence that has been there since the beginning and will be there long after every star has burned out. A machine moving through this space would experience time differently than we do. Not in the relativistic sense, though that plays a role at high speeds, but in the experiential sense. For a human, a decade is a chapter of life, filled with growth and loss and memory. For a machine, a decade is a number in a register. It does not drag, it does not weigh. The machine does not count the days with longing or with dread. It simply persists, taking measurements, adjusting course, monitoring its own health, and waiting for the next thing to observe. Patience for a machine is not a virtue, it is a default state. And in the spaces between the stars, where patience is the only currency that matters, this gives machines an advantage that no biological traveller can match. There is a kind of poetry in this patience. A spacecraft moving through interstellar space at 10%, the speed of light would cover roughly 70 million miles every hour. And yet, from the perspective of the void around it, it would appear almost motionless. The distances are so vast that even tremendous speed seems like stillness. A probe crossing the gap between the Sun and Proxima Centauri would move like a mayfly crossing an ocean, tiny, slow, almost imperceptible against the scale of the water, and yet, given enough time, even the mayfly arrives. That is the essence of robotic interstellar exploration. Not speed, not drama, just time and the willingness to use it. Think of it this way. If the distance from the Sun to the nearest star were scaled down to the width of the United States, from New York to Los Angeles, then Voyager 1, after almost 50 years of flight, would have travelled about the length of a football field. The rest of the journey, the remaining 2,700 miles, stretches ahead, empty and patient, waiting for something with the endurance to cross it. That something will not have a heartbeat. It will not have a name except the one we give it. It will not know what it is doing in the way that we know what we are doing, but it will do it, quietly, steadily, for as long as it takes. There is something poignant about sending intelligence into the void without the body that usually accompanies it. On Earth, minds and bodies are inseparable. Every thought you have is rooted in a physical process, a cascade of electrochemical signals in a brain that weighs about 3 pounds and consumes about 20 watts of power. Your experience of the world is mediated entirely by your senses, by eyes that evolved to see a narrow band of the electromagnetic spectrum, by ears that evolved to hear the vibrations of a specific atmosphere, by skin that evolved to feel the particular warmth and pressure of this particular planet. Take away the body, and the mind, as we understand it, cannot exist. But artificial intelligence is not bound by this constraint. A processor does not need eyes to process an image. It does not need ears to interpret a radio signal. It does not need skin to measure temperature or hands to manipulate an instrument. It can be distributed across multiple physical systems, copied, backed up, resumed after interruption. It can operate in conditions that would destroy any biological organism, in the vacuum of space, in the heat of a stellar corona, in the crushing pressure of a gas giant's atmosphere. It is, in a very real sense, mind without body. And that makes it the ideal explorer of a universe that is almost entirely hostile to bodies like ours. This does not diminish the human role in exploration. We are the ones who ask the questions. We are the ones who design the machines, who choose the destinations, who interpret the data that comes back across the light years. The machines are extensions of our curiosity, not replacements for it. They carry our questions into places where we cannot carry them ourselves. They are our envoys, our scouts, our long patient reach into the dark. The Voyager spacecraft, when their power finally runs out, will go silent. Their instruments will shut down one by one. Their transmitters will fall quiet. But the spacecraft themselves will continue. Metal does not decay in the vacuum of space. There is no oxygen to corrode it, no water to rust it, no wind to wear it down. Voyager 1 and Voyager 2 will drift through the Milky Way for millions of years, perhaps billions, long after the Sun has exhausted its fuel and the Earth has been consumed. They will outlast every human being who has ever lived. They will outlast every building, every book, every memory. They will outlast civilization itself, and they will still be moving, still carrying their golden record, still holding the sound of a heartbeat that stopped beating long ago. And someday, perhaps, the AI probes we send to the stars will join them, not as silent relics, but as active minds, still observing, still measuring, still sending data toward a planet that may or may not still have anyone listening. The thought is strange and stirring. A machine, built by human hands carrying human questions, travelling through a universe that predates humanity by billions of years and will continue long after we are gone. It is the closest thing we have to immortality. Not the immortality of the body, but the immortality of the question, the reaching, the wondering, the refusal to accept that the darkness is final. Perhaps the most remarkable thing about all of this is that it comes from us, from a species that has existed for the blink of a cosmic eye, from primates who evolved on the savannas of East Africa and learned to chip flint and build fires and tell stories under the stars. We cannot cross the distances ourselves. We are too small, too fragile, too brief. But we can build something that can. And in building it, in encoding our curiosity into silicon and launching it into the void, we become something more than we were. We become the species that refused to stay home, not because we left, but because we sent our questions ahead of us, like seeds on the wind, into soil we will never touch. Tonight, as you listen to this, Voyager 1 is moving away from Earth at roughly 38,000 miles per hour. It has been doing this for almost 50 years, and it will continue for as long as the laws of physics allow, which is to say, forever. It does not know it is being thought about. It does not know it carries a golden record with the sound of a human heartbeat. It does not know that back on Earth, people sometimes look up at the sky and think of it. A small, aging machine, farther from home than anything we have ever made, still going, still travelling, still carrying a little piece of us into the vast and patient dark. The machines that follow it will be smarter, faster, more capable. They will carry not just our instruments, but our intelligence, our ability to think and learn and adapt. They will visit worlds we can only imagine. They will see sights that no human eye will ever see. And they will send word back across the trillions of miles in signals so faint that only the most sensitive receivers on Earth can hear them. But someone will be listening. Someone will always be listening, because that is what we do. We build, we send, we wait, and we listen for the echo of our own curiosity, returning from the stars, and on some night far in the future, a receiver on Earth, or on the Moon, or on a space station orbiting a world we have not yet named, will pick up a signal. It will be faint. It will have been travelling for years or decades or centuries. It will carry data from a world that no one alive has ever seen, collected by a machine that was launched by people who are no longer alive. And someone will sit down and open the data and look at the first images of a planet orbiting a distant star. The light will be different there. The colours will be strange. The landscape, if there is one, will be like nothing in any human memory. And the person looking at the images will feel something that is difficult to name. Not pride exactly, not triumph, something quieter, something like gratitude. That someone long ago had the foresight to build a small, patient machine and point it at the dark and let it go. Thank you for listening to Strindberg's Space Stories. If this story meant something to you, subscribing truly helps us keep making these, and I am grateful for every one of you who does. Take care of yourself, and keep looking up.